This is section 5 of thermochemistry. This deals with thermochemical reactions. So we talked a little bit about thermochemical reactions before, and we talked about the fact that you're putting your heat on whichever side it is. If you're endothermic, remember that means that you're going to be a reactant. If you're exothermic, that means you're going to be a product. But you can also use it to do some stoichiometry. So we have an example here of if I take solid carbon, I react it with oxygen gas, I make some carbon dioxide gas, and I'm going to release heat. So the negative indicates, you may want to remember, negative indicates that this reaction is exothermic. And that means it releases heat. What you can do is, when you write your actual thermochemical equations, you can actually think about this as kind of related to each other in moles. So if it's exothermic, that means that when I write it out, my forward reaction, this is a product. So that means if I take 1 mole of carbon, 1 mole of oxygen, I would get 1 mole of CO2, and I would get this much energy. Remember, if these are related to amounts. So if I divided the carbon by half, oxygen by half, CO2 by half, I would also have to divide my heat by half because I would get half as much heat. If I doubled everything, I would have to double my heat because you have to keep the ratio the same. So for every 1 carbon, I get 1 of these. If I have 4 carbons, I have 4 carbons and 4 oxygens, then I would, just like I would get 4 CO2s, I would have to get 4 of these amounts of heat. And you can reverse your reaction. Obviously, if I take 393 kilojoules, I add it to CO2, I could have the reverse reaction and get carbon and oxygen. So that's one thing you definitely want to know about thermochemicals. You can also do it with stoich. So here's an example of how we do it with stoich. It's saying that if I take 2.61 grams of dimethyl ether, which is this guy right here, and we burn it at constant pressure, and again, remember, constant pressure just means that enthalpy and heat are the same. It says that we get 82.5 kilojoules of heat given off, and right here that means that it's negative 82.5 kilojoules. It also means that heat would be part of this reaction here. So I have the ether burning in oxygen, it's giving me CO2, it's giving me water, and I would get heat. And we want to know how to calculate the overall heat of reaction. So what I'm doing is I take my grams of my dimethyl ether, and I say that for 1 mole of dimethyl ether, the molar mass is 46 grams. Again, like in honors chem, just look it up on the periodic table, and I get my moles of dimethyl ether. Then, since what I'm looking at here is that's how much energy I get from this much dimethyl ether, what I'm doing is I'm taking that negative 82.5 kilojoules and I'm dividing it by the moles of my dimethyl ether. And what I find is that I would get negative 1460 kilojoules per mole of dimethyl ether that was being released. And if you look at the equation, that's okay because there's 1 mole of dimethyl ether. If say there was like a 7 in the balanced equation, I would have to multiply this by 7 to put it in the reaction. If there was like a 1/2 in front of my dimethyl ether, I'd have to multiply this by 1/2 so that I would keep it the ratio for the same. But since this is per mole of dimethyl ether and my reaction is 1 mole of dimethyl ether, what I do for the thermochemical, I just say, okay, I have 1 mole of dimethyl ether, I have 3 oxygens, I'm going to make 2 CO2s, 3 waters, and again, since it's exothermic, it's releasing heat, that 1460 kilojoules goes on the right. And you can say this in regards to anything. We could say that there's 1460 kilojoules for every 3 moles of water that are released. We could say there's 1460 kilojoules of heat released for every 3 moles of oxygen that are burned. So you can relate it to anything in that reaction once you have it written, but you have to make sure you write it correctly. And last slide for this section, just another one of these. We want to know how much heat's released if we burn gasoline. So we have pure isooctane, C8H18, we burn it. And this is the overall thing. So, and when they give you the delta heat of reaction, what they're really giving you is for like the balanced equation. So this is our balanced equation right here. 2 moles of the isooctane, 25 moles of oxygen, 16 moles of CO2, 18 moles of water. We could add on here, because this is definitely exothermic, plus 5,460 kilojoules. And then that would be for the thing. So what we have here is we have 692 grams of gas. And again, we're going to need to get into moles. So there's 1 mole of gas for 114 grams. And then we know that we have negative 5,460 kilojoules for the 2 moles of gas that are in this reaction. And again, this is really just like a mole ratio kind of situation. And what we find out is we're going to get negative 16,600 kilojoules released. And again, you're just using this balanced equation here. Like if we were doing oxygen, then 25 would be on the bottom. If we were using CO2, then 16 would be on the bottom. And then if you look here, we want to write a thermochemical equation for only 1 mole of isooctane. So what we have to do here is look at our balanced equation. See that, okay, obviously we're double, so we have to half all the coefficients, which means we also have to half the heat so that we're fair and keep our ratio the same. This is a tricky topic for some people because you have to keep thinking about that ratio that you can't change. So you'll just have to make sure you're really working on it. Again, your book is an excellent resource for this.